Lastly, we are going to cover energy and physical changes, and we will finish chapter 7. Energy is the ability to produce heat or to do work. That is the definition we're going to work with. The SI unit of energy is the joule. We also know of calories, although these are not the same as calories that we know from food. Here's the relationship between 1 calorie and joule. What is the relationship between them? The conversion factor, if you will. 1 calorie is equal to 4.184 joules. And you will have to have this handy. You may have to use it. So write it down somewhere and have it handy to use. We also should know that 1 kilojoule, little k, big J, so capital J, 1 kilojoule is equal to 1,000 joules. The kilo stands for 1,000. 1 kilocalorie, this is really the calories in food that we see in the labels of anything related to food. 1 kilocalorie, the same thing. The kilo stands for 1,000 calories. So these are the same, really, 1,000, but one is joules and one is calories. We are going to use this equation here to figure out the amount of energy that is required to increase or decrease the temperature of a particular substance, the mass of a particular substance by a certain temperature. So we talk about specific heat capacities, or just specific heat for short, of different substances. And every substance has a specific heat capacity that is unique to them. And that depends on the type of molecule they are. What is a specific heat capacity? That is the amount of energy that is required to increase the temperature of 1 gram of that substance by 1 degrees Celsius or Kelvin is the same thing. And here is what this here translates into this equation mathematically. So Q is equal to the specific heat multiplied by the mass multiplied by change in temperature. Now, the specific heat is defined as the energy that is required to increase the temperature, so delta T to be 1, so 1 degree of 1 gram, so 1 gram of a substance. So M1, delta T is 1, specific heat capacity then is equal to the heat, the amount of heat. Make sure that you have this equation handy because we are going to be using this to do calculations. Here are some specific heat values, and you can find more tables that contain specific heat online if you search. But we have different substances listed, and these are the specific heat. What I want you to take out of this table is that some substances, like water, for example, have a very high specific heat, and other ones, like the metals, have low specific heats. What does that mean? Qualitatively speaking, it means that it takes a lot more energy to increase the temperature of 1 gram of water by 1 degree than it takes gold. So that's what the relative, so the specific heats tell me. That is why the water it's got a high specific heat, and it's such a good insulator, if you will. It helps to temper those increases and decreases in temperature that we would otherwise have without having water. That's why water of the oceans helps to regulate the climate and the temperature of our planet, because it can absorb so much heat and not increase the temperature as much, right? It takes a very large amount of heat, of energy, to increase the temperature of water. And if we didn't have water, for example, but we had just rock, then that specific heat would be so much smaller. So, or asphalt, we have all noticed how hot asphalt gets in the summer. Why? Because its specific heat is very small. And so it doesn't take much energy to raise its temperature. And that is why we're blessed to have a lot of water on our planet, and that tempers the temperature so much. Calculate the amount of energy in kilojoules that is required to increase the temperature of 255 grams of water from 25.2 degrees Celsius to 90.5 degrees Celsius. I will do this example problem for you, and then you can do the next one. So what am I asked? I am asked to figure out the energy, Q, in kilojoules. First, I will calculate it in joules, just because that's how Q equals mc delta T is set up. And then I can convert it to kilojoules. But I'm asked to find Q when I know the mass of water, and I also know the temperature change from 25.2 to 90.5. I'm going to use this particular formula. So I have Q, that is my energy. It's equal to the specific heat capacity for water, and I can look that up from the table, multiplied by the mass of water in grams, which I have, multiplied by the change in temperature. Well, I can calculate that. Change in temperature is really final temperature minus initial temperature. This is my final, this is my initial. So if I take the difference of those two, I will have the delta T. Delta, this Greek symbol here, delta stands for change. So the difference, change in temperature. So here it is. Q is equal to 4.184 joules per gram per degree Celsius. This is the specific heat capacity of water, and I took that from the table, but these are the units for every specific heat capacity. It's joules over gram over degree Celsius. Now I multiplied the specific heat capacity by the mass, which is 255 grams. And I also multiplied by the change in temperature, which is 65.3 degrees Celsius. So if I take 90.5 minus 25.2, I get 65.3 degrees Celsius. Note that I'm multiplying and dividing by degrees Celsius, so this will cancel out. I'm also multiplying and dividing by the mass in grams, so that will cancel out as well. Then if I just do 4.184 times 255 times 65.3, I get this value in joules. However, the problem told me I needed to find the energy in kilojoules. So I take this amount in joules divided by 1,000, because that's what the kilo stands for, divided by 1,000, it will give me 69.7 kilojoules. Now, this is something that we haven't talked about in a while, but this is also expressed in 3 significant figures, because I have 3 significant figures here, 3 here, and 3 here. And therefore, my answer has 3 significant digits. Q is always expressed in joules. Mass is expressed in grams or kilograms, but you would have to convert it for this particular formula. You'd convert it to grams. And delta T will be either in Celsius or in Kelvin. The specific heat capacity is going to have units of joules per gram per degree Celsius. Here is a sample problem that is very similar to the one we just did. Calculate the amount of energy in kilojoules required to increase the temperature of 180 grams of copper from 50 degrees to 972 degrees Celsius. The specific heat of copper is this. Note that this is multiplied, right? Joules is divided by both grams and degrees Celsius, but grams and degrees are multiplied together. Okay, just follow along like we did to the previous example problem that I showed you, and this is no different. Now let's talk about phase changes. The first phase change that we're going to talk about are melting and freezing. These are opposite sides or different faces of the same coin. So they're opposite of each other, right? What is melting? We are familiar with what these are. Melting is when we're going from solid to liquid phase, and freezing is the opposite, is when we're going from liquid to solid. Note that melting is also known as fusion. So those are interchangeable terms. Okay. Note that if I'm going from solid to liquid, I have to add external energy. So if it's melting, right, if I am melting a solid, I'm taking it from solid to liquid phase, I have to add energy. If I'm going from liquid back to solid, then that energy is given back to me, to the outside, right? The solid has to grab energy from the outside of itself to melt into a liquid. When the liquid freezes and goes into solid, it gives off that energy. Heat of fusion or melting is the energy that is required to melt a solid. Okay? Heats of fusion are given in molar quantities, not in grams, like we did for the other heat energy. So molar heat of fusion, delta H of fusion, is the amount of energy that is required to melt 1 mole of a substance, and it's expressed in kilojoules per mole. Here is the formula that we're going to use to calculate the heat of fusion. That is the molar heat of fusion, delta H, times how many moles of the substance we have. Note that if I have an amount given in grams, I first have to calculate the molar mass of the substance and convert that to moles, and then I can use this formula. Here are some delta H fusions for different molecules like argon, benzene, etc., etc. So these values will be given to you in a table. Once you have the delta H of fusion, if you know the moles of the substance or even grams of a substance, you can calculate moles from grams using the molar mass, and then if you have delta H, you can then figure out how much energy does it take to melt that many moles of that substance. We can also talk of two different processes in terms of energy. We talk about exothermic and endothermic processes. Exothermic, exo meaning out. An exothermic process is a process that gives off energy. So it releases energy into the surrounding. The endothermic, endo meaning inside, the endothermic process actually needs to grab energy from the outside for it to happen. So if I'm changing a substance from the solid phase into a liquid phase, remember we talked about in the previous slides that to go from solid to liquid, the solid needs to grab energy from the outside. That means it's an endothermic process. It needs to grab energy from outside of itself. We must add heat to the solid to be able to melt. If, on the other hand, I'm changing the substance from the liquid back to the solid phase, that is an exothermic process. The liquid has to give off heat as it is freezing back into the solid state. So it gives off its own heat back to the surrounding, and that is an exo meaning out. It gives out or gives off heat, and it's the opposite of the endothermic process. Let's talk about vaporization. Vaporization is going from the liquid phase to the gaseous phase or vapor phase. Once again, vaporization is an endothermic process. It needs energy from the outside. So the liquid, to be able to go into the vapor phase, it needs energy. And typically we do that, for example, if I'm evaporating water. Now I can just leave it on the countertop, but it's sped up quite a bit by using the stove, right? I can boil the liquid and evaporate, make sure those molecules have enough energy to go into the vapor phase. So if the molecules in a liquid have enough energy to break free of those intermolecular forces that are holding them in the liquid, then they can evaporate, they can move into the vapor phase. As I said earlier, vaporization is an endothermic process. What is the opposite of vaporization? That's condensation. And condensation is going from vapor to liquid, and it's an exothermic process. Here it is. Condensation is going from vapor back to liquid, and it gives off energy, so it is an exothermic process. When we calculate heat of vaporization, just like heat of fusion, this is the energy that is required to vaporize a mole of liquid, meaning if I take a mole of liquid and I move a mole of those molecules into the gaseous phase, vaporize them, so make them vapor, that energy that is required to do that is the molar heat of vaporization, or delta H vap for vaporization. It's also expressed in kilojoules per mole. That's because it takes a lot of energy to do that, and that's why Q is large, and we express them to help us. We write them in kilojoules instead of joules because they would be large numbers in joules. So Q is equal to delta H vaporization times the moles of substance. This follows the same format as the delta H of fusion. Here is another table that has substances listed and delta H of vaporization for those. Note that the delta H of vaporizations are much larger than delta H of fusion. That is because it takes a lot more energy to take those molecules from the liquid phase and pull them apart into the gaseous phase. So it takes a lot more energy, and that's why delta H of vaporization is much larger than delta H of fusion. Lastly, the last phase changes we're going to talk about is sublimation and deposition. These also are related. They're opposite. They go in opposite direction. Sublimation is the transition directly from solid phase to vapor phase without first becoming liquid. That requires very specific conditions of pressure and temperature, but it can happen. We all are aware of, because we've seen it, of dry ice. Dry ice is really CO2 that is solid and is going into the vapor, is subliming, it's going directly into the vapor phase without it melting first. The opposite process then is called the deposition. So the deposition is where the gaseous molecules deposit, if you will. They become arranged and form the solid, right? Become orderly and deposit themselves into the solid phase. The deposition is an exothermic process where sublimation is endothermic. Okay, so sublimation is endothermic because the solid needs energy to move. Those molecules need energy to overcome intermolecular forces to move into the vapor phase. But deposition is opposite, is the exothermic. That energy that the molecules have in the vapor phase needs to be given off before they can actually be deposited back into the solid phase. Here's kind of a diagram that illustrates the phase changes and the direction that we go. And this is dependent on the temperature, right? As we increase the temperature, we go from solid to liquid to gas. Melting, what's happening during melting and vaporization, sublimation, deposition, or condensation and freezing. Here's a sample problem For each process, determine whether energy is given off or it is required. So basically, is it exothermic, gives off energy, or required, endothermic, and the quantity or the amount of energy that is involved. I picked this one for you. I'm going to do one where you start out with grams. If you start out with moles, you don't have to do an extra step, but if you do start out with grams, you will first have to convert the grams to moles. So here it is. I take the amount of grams of methane, and I know the molar mass of methane, which is CH4. I could calculate it to be 16.04 grams per mole. So methane will cancel, the grams will cancel, leaving me with moles of methane. And then from the table, I know that it takes 0.84 kilojoules to raise the temperature or to melt 1 mole of methane. And so I can use that value to figure out how much energy is required since I'm melting, okay, from the solid to the liquid. To go from a solid to a liquid, I need to add energy, so it is required. And the moles will cancel with moles, leaving me with kilojoules. So if I do 73.2 times 0.84 divided by 16.04 will give me 3.8 kilojoules. Note that everything else cancels out except for kilojoules. Now do the same thing for the benzene and ethanol. You don't have to worry about converting these, doing this step right here because it's already at in moles, but figure out using those values, delta H's from the tables to figure out how much energy, whether it's given off or required as well.